Okay, class, we continue our class online. In the previous lecture, I have given you this question for you to calculate the alkalinity. So today, I would like to start on how to calculate the alkalinity. So the best way is for you to list down the concentration of species or chemical species that you are going to calculate. So you can start with writing down the equation for alkalinity. So from here, you need to calculate hydroxide ion concentration, the bicarbonate concentration, and the hydrogen ion concentration. So how to do it? So I have listed down one by one. So, but the water sample is come with the pH of 8 or having a pH of 8. So based on this, you can calculate the concentration of hydrogen ion. So I hope that you still remember pH plus POH, which is equal to 14. And then pH is equal to negative log hydrogen ion concentration. So in this case, it's 8. So the hydrogen ion concentration will be equal to 10 to the power of negative 8. So by using the pH plus POH is equal to 14, so the hydroxide ion concentration would be 10 to the power of negative 6. So all these add up together will become 14. And then the bicarbonate concentration is given 1.5 micromolar. So I have converted it into 1.5 times 10 to the power of negative 6 molar, which is to make the calculation easier. And then for the carbonate, it is not so straightforward. You have to write down the equilibrium equation for this. And then the water concentration, you can put it as 1. So in this case, the constant is given is 4.7 times 10 to the power negative 11 times the concentration of bicarbonate divided by the concentration of hydrogen ion. You're going to get 7.05 times 10 to the power negative 9. Okay, so the next step will be the calculation of alkalinity, where you insert all the concentration that you have calculated here into the equation. So what you are going to get as the first answer would be 2.5 times 10 to the power negative 6 molar. As I have shown in the previous slide, so the alkalinity basically is most of the time is presented in milligram per liter of calcium carbonate. So what you can do here is you just time the relative molecular mass of calcium carbonate, which is 100, and then it will become 2.5 times 10 to the power negative 4 gram per liter. We can turn it into milligram per liter, which is a common unit for alkalinity. So the answer is 0.25 milligram per liter of calcium carbonate. Okay, so if you are not sure about anything about the calculation, please feel free to contact me. We will quickly move to the next topic, water hardness. I'm not sure you have seen this the condition before or not. So the first one, you can see the kettle is coated with something, and then the bathtub turned into yellow color. This one is not common because it is a soap. When you mix with water, you stir it, you're supposed to get bubble, but in this case, the bubble are not formed. So why this thing happen? Is because of the water containing high amount of calcium. So as I always mention in the class, so water is actually exposed to the rocks. So the rocks have different type of minerals, especially the calcium mineral, and the calcium will especially the calcium carbonate. So the calcium carbonate can dissolve in water. So there are many types of mineral available in the nature. So for example, gypsum, dolomite, calcite, aragonite. So all of these are different forms of calcium carbonate mineral. So water hardness is actually referring to the measurement of the amount of calcium and magnesium salt in water. So I have one example here. This data is from UK. So you can see how they categorize the water hardness. So from here 0 to 50 they categorize as soft, 100 to 150 slightly hard, and then 200 to 300 hard, and then more than 300 they call it very hard. You can see here the concentration is actually just like alkalinity is presented in milligram per liter of calcium carbonate. Okay, is hard water harmful? Basically, it's just containing the mineral. Calcium is not harmful to us. Okay, but it will be harmful to the industrial process, especially those industry that involve the usage of boiler or cooling tower. So you can see here, the mineral is actually precipitated in the boiler, or it can even form a scale. So when something is coated on the heating element or heating coil, then we need to supply more energy to boil the water. So it will increase the operational cost. Okay, so we come to the calculation to see how we can calculate the total hardness. So I have a few examples here, 4 examples. Before that, as I mentioned just now, water hardness is referring to calcium and magnesium. So basically, if you want to do the calculation, make sure don't include other ions. You just calculate the magnesium and calcium. So you can take a look on this. The first example is, you can imagine the water is containing 50 milligram per liter of magnesium carbonate. So what is the water hardness for this sample? So to calculate it is very easy. So 50 milligram per liter, just divide by the relative molecular mass of magnesium carbonate, which is 84.3, and then you are going to get 0.59 millimolar. So which is this one. You can try to calculate. And then, of course, it is in the forms of molar. You have to convert it into milligram per liter of calcium carbonate, right? So to do that, you just need to time 100. Oops, sorry. You just need to time 100. And then what you are going to get is 59 milligram per liter of calcium carbonate. So the second example will be the mixture, the water that containing the mixture of 21.1 milligram per liter of magnesium carbonate and 25 milligram per liter of calcium carbonate. So you have to convert it one by one into a molar. So for example, magnesium carbonate here, 21.1 milligram is equivalent to 0.25 millimolar. And then 25 milligram per liter of calcium carbonate is actually equivalent to 0.25 millimolar. So change to molar first and add it up. So in this case, you will get total of 0.5 millimolar. So from here, if you want to convert it into the milligram per liter of calcium carbonate, you just need to times 100. So you'll get 50 milligram per liter of calcium carbonate. So you can try to calculate the C and D. Okay. Okay, so we have come to the last topic, which is metal and complexation in the environment. So far, we have went through organic matter pollution, thermal pollution, acid pollution, and this would be the last part, heavy metal pollution. You can try to Google what is heavy metal pollution. I believe you're going to get a lot of news saying that the seafood is actually contaminated with heavy metal. So it has become a very serious and visible environmental contamination or pollution. So you can see here, heavy metal contamination, serious and remarkable concentration of arsenic, lead, and cadmium in Turkish fish. And then heavy metal threat to shellfish. And then this is another example in India where the seafood is actually containing high amount of metals. And then they have found that heavy metal pollution is weakening the scallop shell and threatening their survival. So why? Where is those heavy metal coming from? Well, basically it's due to the human activities that release the heavy metal into the water. But we know that all this seafood or the aquatic organism is actually living in the water. They can't run away from the water. So the water will pass through their body and slowly accumulate in their body. So if you eat this seafood, the heavy metal will transfer to your body. So what is heavy metal? Heavy metal is actually referring to the transition metal. So this is the transition metal. Okay. So other example instead of seafood is the groundwater contamination in Bangladesh and Eastern India, where the water is actually contaminated by arsenic. So they have no choice. The villagers have to rely on the water, the groundwater, because they do not receive any tap water or treated water. So in this case, they have to drink the water, which is containing arsenics. So this arsenic have caused the skin lesion and even the death. So just take a look on this. So this is how the skin lesion look like. So of course, another example is the one that I showed you at the very beginning of the lecture, the mercury pollution, which caused the Minamata disease. So this metal is actually attacking the nervous system of human. So in most of the fresh water, the concentration of this heavy metal is actually very small. So in the range of microgram per liter or nanogram per liter. So as compared to calcium, which appear in milligram per liter. So this metal has been the interest of study because first of all, it's toxic. It can influence the biological process. And the second one, it can interact with any solid phase in the environment. So metals such as copper, zinc, calcium, or potassium, it is a nutrient for the plant. But some of the metal, when it appear in excess amount, it will turn into toxic. So especially like copper and zinc. So some metals like cadmium and mercury, it can be very toxic at a very low concentration. So metal, it can appear in aqueous environment in various forms. It can appear as free ion, it can appear as aqua complexes, it can appear as a complex with inorganic ligands such as chloride and carbonate. And then it can also complex with natural occurring organic molecule. So we are going to focus on this later. Okay, before we move to the natural occurring ligand, so just take a look on the iron tree. So iron tree is a very common mineral in water. When it's first dissolved in water, it can form the hydrated ion, and slowly, or not hydrated ion, it's actually aqua complexes. This is aqua complexes, and then the aqua complexes can slowly ionize and turn into different complex ion. So you can see here, this is actually a simplified form where it's written without water. Please don't worry about the calculation. I'm not going to question this in final exam. So what I want to show you is actually the solubility of this species. So you can look up from here, iron 3 plus itself is not soluble in water. If you put in the iron 3 plus into water, so most likely it will stay in the form of solid. So the soluble part, the concentration is in the range of 1.6 times 10 to the power negative 18 molar. Okay, so which is very small. So how about their complex? So when they turn into aqua complexes and start to be ionized, so the concentration of this metal ion in water can increase. So from negative 18 to negative 13 to negative 10. So in other words, these metal ions, even though it's not soluble in water, but it have a tendency to form complex and soluble in water. So later on, we will try to look at on how the natural organic metal can form complex with metals and influence their solubility in water. Okay, so we come to the topic of natural chelating agent, which is humid substances. So the most important class, this humid substances is the most important class of natural ligand, or the ligand that occur naturally. So where is this humid substances coming from? It is actually coming from a plant material, a degradation resistant material, or I would say degradation resistant plant material. So we know that in the jungle, in the nature, we have dead leaf, dead branches that will fall on the soil surface. So once it reaches the soil surface, it will be slowly decomposed by environment or as well as the microorganism. But up to a certain structure, when it's degrade up to a certain level, it will stop. So it will, or in other words, it's partially degrade. So these material are such as peat, coal, lignite. So it can bound naturally to the soil as well as water. Just take a look what is peat. Peat is very simple. I think most of you know that peat is tanah gambut. So it's actually formed through, it's actually mixture of soil with the plant material that bury under the surface. So this peat, after a very long period of time under pressure and heat, it will slowly turn to the coal. It will turn to the lignite and coal. So basically all of this is come from a plant material. Okay, so we have three types of humid substances. The first one is called humine, second one is called humic acid, and the third one is called fulvic acid. So this is the example for parts of humic acid. So let's take a look on what is the difference between these three. You have to imagine you have a soil sample which is coated with humid substances. So in this case, you put the soil into a conical flask and then soak with sodium hydroxide and shake it. So after that, whatever it can soluble, it will soluble in the solution. The non-soluble part is actually the soil that coating with humine. Okay, humine. So the soluble part will be in the solution. You can imagine you just filter it off. You take the solution, then you add acid. So when you add acid, the humic acid, because it's acid soluble in base. So when the solution turn into acid, then the humic acid will precipitate as solid. Okay, fulvic acid will be the one that remain in the solution. Where it is very soluble in the water, it will not precipitate. Okay, so I hope that you can differentiate between these humine, humic acid, and fulvic acid. So let's take a look on the structure of a humic acid molecule. So it's a huge molecule. Just now I said it's come from the plant material, right? So you can see here, this is a plant lignin. So where you can find a lot on the skin of the plant or the tree. So the structure is almost similar, but it's partially decomposed. Part of the aromatic is actually opened out and turned into aromatics. So this molecule is large. So far, we do not have a technique which allow us to identify the structure. So what scientists will do is they break the humic acid down into pieces and analyze it part by part. So after they get the structure, they will just like a jigsaw puzzle, they put it back and propose the structure. That is the reason why it's called proposed structure. It's not absolute structure for the humic acid. And then let's take a look on the fulvic acid. Fulvic acid is much more smaller and it is very soluble in water. Just take a look on the functional group that it has. Okay. Okay. Are you going to, I don't think you are going to memorize all the structure, right? So, but the most important thing is you have to understand what is the functional group that that associated with the humic acid, humine, and fulvic acid. So just take a look. Most of it is consisted of, for example, ketone, carboxylic acid, hydroxy group. So it's also same as for the fulvic acid. Okay. So this functional group is actually important for it to complex with metal. So I have summarized the structure here. For example, the first one is containing carboxylic acid and hydroxy group. So you can see here, it has a lone pair electron that can be donated to metal. The second one is 2 carboxylic acid group. The third one is showing the electron-rich aromatic ring, which can donate the electron to the metal. So all these are complexation. So of course, if the functional group is ionized, it also have the tendency to interact with metal ion under ionic interaction. As I mentioned just now, fulvic acid is very soluble in water. So when it's complex with metal, it will solubilize the metals. Or in other words, it causes the metal to be soluble in water. Humine and humic acid is actually solid. So if you have water that containing heavy metal, when it is in contact with insoluble humine and humic acid will complex with the metal and remove it from water. So now the water will be clean because the metal has been transferred to the insoluble humine and humic acid. So in other words, fulvic acid increase the solubility of metal, and humine and humic acid will decrease the concentration of metal in water. So we have done with the natural ligand. Now we take a look on the synthetic chelating agent. So synthetic chelating agent, it is actually a man-made chemical such as EDTA, NTA. It has been found in a lot of sewage effluent and industrial wastewater. For those who have attended the lab, the analysis lab, you know what is EDTA. So you use this for the complexation titration. So EDTA is, the full name is ethylene diamine tetraacetic acid. So you have ethylene here, CS2, and then you have 2 amine, we call it diamine, tetraacetic acid, you have 4 groups of the acetic acid. So you can see from this structure, all these oxygen atoms and nitrogen atom, it can donate its lone pair electron to metal. So for NTA, it is it's called nitro triacetate. So we have 1 nitrogen group and 3 acetate group. So all these chelating agent is very soluble in water. So just take a look on what is the application of the EDTA and NTA in the industry. EDTA has been used in the textile industry to solubilize metal. So textile, we know that they want to color the shirt or the clothes. So they will use a lot of dye. So the dye, when it's complex with metal, it will change color. So to avoid that, EDTA will be added to make sure those heavy metal is soluble. And then it will not complex with the dye. And then it also has been used in the paper industry to remove or to solubilize manganese. So this manganese will cause the catalytic activity and color the paper. So without adding the EDTA, most likely this manganese will cause the to cause the paper to turn into a brown color. So it also has been used as a stabilizer in food. This example is also saying that to remove the metal ion so that the color of the food will not change. So that is the reason why it's called a stabilizer. So it also has been used in cosmetic, food, and medicine and laboratory. So I have one example here, which is a food that's showing is containing calcium, disodium, EDTA. So the EDTA is here. So how about NTA? NTA, it has been used in industry for the treatment of hard water added to a boiler water. So just go back to the previous slide. Okay, so you can see here without water softener, so the mineral will precipitate everywhere. So with water softener, this one is actually NTA. When it's added, it solubilizes the calcium so that the calcium will remain in water and not precipitated out. Uh, so based on the EDTA, we can say that it is actually not harmful to human. But when EDTA appear or the synthetic chelating agent appear in the environment, then it will become a pollutant. Why I say so? Because the EDTA that occur or appear in water, it have the tendency to dissolve radioactive cobalt and plutonium and increase the migration rate of this radioactive material into the water. So in terms of wastewater treatment, we know that nowadays we still have a lots of this metal pipe. So if the water containing EDTA and move along this metal pipe, it has the tendency to solubilize the metal like lead and iron. And then it can also cause the increase in the leaching of metals from the waste disposal site, reduce the efficiency of heavy metal removal via sludge. So this is one, you will know what is sludge later on when we come to the next topic. So basically, we rely on the removal of the sludge and at the same time remove the heavy metal. We hope that this sludge will bind with the heavy metal. If the EDTA appear in the water, it will cause the heavy metal to soluble in water. Then it will not be easy to remove. And then it can also increase the macronutrient of the algae, because since it can keep the iron 3 soluble in water. This will be the last slide. Don't worry about the calculation here. What I want to show is the tendency for NTA or EDTA to complex with metal. So we have a case study, solubilization of lead by NTA. So we know that NTA is having 3 acetate group. So if this 3 acetate group is not soluble, is not ionized, then you are going to have 3 hydrogen ion that bind to the NTA. So if you look at this first variable diagram here, when the pH increase, this NTA will start to ionize. So it's released the first proton at pH around 1 to 4 and slowly release the second proton, and the last one will when it's released all the proton. So if we talk about our natural water, so most likely this NTA will appear in this form. So what if the water that containing NTA that pass through a lead pipe or the pipe that containing lead? So the calculation based on this showing that when you have the NTA that in contact with lead, the tendency for it to form complex is 207 to 1. Okay, so which is very high. Almost certain, almost immediately, those lead will turn into water-soluble lead complexes or complex. So in this case, it will increase the toxicity of water. If you still remember, I said that for substances to be toxic, it need to be soluble in water first. So the presence of NTA, it will increase the solubility of lead in water. So with this, I end the lecture for hydrosphere.